Imagine three very different fuels on a truck: a bale of wood chips, a bag of mixed household trash, and a load of plastic waste. All three can end up in the same kind of system: a waste to energy plant with combined heat and power. When most people hear waste to energy, they picture a smokestack and a boiler. From an energy engineer's point of view, this is only half of the story. In this video, we will explain step by step how these plants work and how they treat biomass, plastics, or a mix of both, like in municipal solid waste. When engineers say waste to energy plus CHP, they usually mean a boiler that burns waste and biomass plus a steam turbine that produces both electricity and useful heat. Compared with a normal power plant, it uses fuel more efficiently because the heat that would usually be wasted is delivered to homes, industry, or district heating. The input for these plants can be mixed municipal solid waste, dedicated biomass, or RDF SRF, refuse-derived fuels that are often plastic-rich after pretreatment. Traditional heat and power systems are between 45 and 51% efficient. With the implementation of a CHP system, that efficiency can increase to 75 to 80%, significantly reducing the amount of energy used by industrial facilities. Worldwide, more than 1,100 WTE plants are currently in operation, with a combined treatment capacity of more than 700,000 tons of municipal waste per day. The most common pathway is a classic waste-to-energy incineration plant. In the past, waste incinerators had a bad reputation because they had little or no flue gas cleaning and caused a lot of air pollution. Today, modern WTE plants must meet very strict emission limits, such as those in European Union legislation, so incineration is now much cleaner than it used to be, but it's still weak on circularity. It burns valuable materials, which goes against effort to reduce waste and increase recycling. So, how do these plants work? Waste is burned on a moving grate with excess air, reaching bed temperatures of 850 to 1050 degrees Celsius. Hot flue gases passes a water tube boiler, producing steam, often between 380 to 420 degrees Celsius at 30 to 45 bars in conservative designs. Steam goes through a condensing turbine to make electricity. After the turbine, the steam is fully condensed with cooling water and the heat is dumped into the river or air. These steam conditions are not limited by turbine technology. They are limited by corrosion and fouling caused by chlorine, alkali metals, and heavy metals in the waste. In the CHP integration, the steam drives a back pressure or extraction condensing turbine. Electricity efficiency alone might be 20 to 25%, but if you take exhaust steam at, for example, 3 to 5 bar and send it to a district heating network, you can reach total efficiencies of 75 to 80%. In this configuration, you get slightly less electricity, but you also sell the heat, so total energy efficiency is much higher. This pathway is robust to variable feedstock and is still the workhorse for mixed municipal solid waste in dense cities. The second pathway is fluidized bed combustion of more homogeneous waste fuels like refuse-derived fuel, RDF, or biomass-rich fractions. In a bubbling or circulating fluidized bed, sand or bed materials are fluidized by air. Operating temperatures are typically 800 to 900 degrees Celsius, and because the fuel is more homogeneous and contaminants are lower, you can usually push to higher steam parameters. For example, 450 to 500 degrees Celsius and 60 to 90 bars can help improve electrical efficiency. Typical uses for these plants include industrial combined heat and power, where a cement plant, paper mill, or chemical plant takes the medium pressure steam for its own processes. Key differences from grate incineration are that fuel must be prepared first. It is shredded, metals are removed, and it is often sorted by size and sometimes by a chlorine content. Fluidized beds are more sensitive to bed agglomeration. from alkali metals, sulfur chlorine chemistry. So the pretreatment and fuel specification are key. Here are 2 points to consider for the future of incineration. Carbon accounting is changing the game. Waste contains materials that are derived from fossil fuels like plastics. Energy produced from waste incinerators is therefore not totally clean or renewable. So incineration plants are under pressure to document the biogenic versus fossil share of the waste. This decides whether the electricity and heat are counted as renewable energy under national schemes. Integration with industrial clusters. The most interesting projects nowadays are not standalone WTE plants, but nodes in industrial clusters. For example, low pressure steam to a food factory, high temperature heat to a chemical plant, biogenic CO2 from flue gas capture to a nearby greenhouse. Technically and commercially, WTE is still the most mature option for large-scale treatment of mixed waste and biomass, especially when you can connect to a district heating network or industrial heat users. It can handle biomass and plastic together in one robust system. But it is fundamentally a destructive pathway. It recovers energy well, yet it destroys the material value of plastics and waste. In the next videos, we'll look at more advanced technology that turn waste into higher value products, going beyond just heat and power.